everyone. This is group number 6 from Division H, Vishwakarma Institute of Technology, Pune. In this video, we will be explaining the working of DMA transfer. What is DMA controller? DMA controller is a type of control unit that works as an interface for the data bus and the I/O devices. As mentioned, DMA controller has the work of transferring the data without the intervention of the processors. Processors can control the data transfer. DMA controller also contains an address unit which generates the address and selects an I/O device for the transfer of data.
Moving on to working of DMA. DMA controllers work under the CPU. Although data transfer via DMA happens without the involvement of the CPU, it facilitates an interface between the I/O devices and the bus. We can connect more than one external device with DMA. DMA controllers also contain three registers: address, word count, and control registers. In order to find the target location in the memory, we use the address register. The word count register counts the number of words in input data that needs to be transferred. Finally, the transfer mode is specified by the control register. Now let's take a look at the block diagram of DMA controller in order to explore the working procedure in more detail. In order to make a successful data transfer, DMA must share the bus with the CPU. Now let's assume we are about to transfer data from an I/O device to memory. In this situation, the CPU forces the current program to stop. Additionally, the CPU increments the value of program counter by 1. Furthermore, the CPU generates a signal and sends it to the DMA controller over the address bus. Now, if the DMA controller accepts the signal, it generates a bus request signal. Additionally, a request is sent from the DMA controller to the CPU in order to control the bus. The DMA controller becomes the bus master if the CPU grants the request. Furthermore, the CPU sends the address in the memory, the direction of data transfer, and the number of blocks in the data. After initializing the data transfer task to the DMA controller, the CPU resumes execution.
Now, after getting some brief idea about DMA and its working, it's time to analyze modes of DMA transfer. But before that, let's understand why we need to study mode of DMA transfer. So, during the DMA transfer, CPU can perform only those operations in which it doesn't require the access of system bus, which means mostly CPU will be in block state. And for how much time CPU will remain in block state, or in other words, for how much time CPU will give control to DMAC, that is direct memory access control of system buses, will actually depend upon the following modes of DMA transfer. And after that, CPU will take back control of system buses from DMAC. Now let's see first mode of DMA transfer, that is burst mode. In this mode, burst of data is transferred before CPU takes control of buses back from DMAC. Here, burst of data can be entire data or burst of block that contains data. Here, we can also calculate percentage of time for which CPU will remain in block state by simple formula. So let's see it. So time taken to prepare data be Tx and time taken to transfer data be Ty. Then percentage of time CPU will remain blocked due to DMA is as follows: Ty divided by Tx plus Ty whole bracket into 100. So here we have finished first mode of DMA transfer.
The next mode, that is mode number 2, cycle stealing mode. Slow input output device will take some time to prepare data or word, and within that time CPU keeps the control of the buses. Once the data or the word is ready, CPU gives back control of the system bus to the DMAC for one cycle, in which the prepared word is transferred to memory. As compared to burst mode, this mode is little bit slower since it requires little bit of time which is actually consumed by input-output device while preparing the data. The next mode, that is mode number 3, is interleaving mode. Whenever CPU does not require the system buses, then only control of the bus will be given to DMAC. In this mode, CPU will not be blocked due to DMA at all. This is the slowest mode of DMA transfer since DMAC has to wait might be for so long time to just even get the access of system bus from the CPU itself. Hence, due to which less amount of data will be transferred.
Now we'll be looking at the pros and cons of the three modes. The first is cycle stealing mode. Pros. This mode is simple and inexpensive. It can be used in systems with low DMA requirements and doesn't require any special hardware support. Cons. This mode can cause performance degradation for the CPU since it is halted during the DMA transfer. Also, this mode is not efficient for transferring large amounts of data. The second is burst mode. Pros. This mode is more efficient than cycle stealing mode for transferring large amounts of data. Cons. This mode requires hardware support for bus mastering and is more complex than cycle stealing mode. Third, demand mode. Pros. This mode is flexible and can be used in systems with unpredictable data transfer rates. Cons. This mode is more complex than cycle stealing mode and requires hardware support for bus mastering. It can also cause performance degradation for if the DMA transfer rate is high.
In start of video, we all are acquainted with working of DMA, direct memory access, and all its fundamentals. Now we will see an example in order to make our concept crystal clear. Now let's move to question. A DMA controller transfers 16-bit words to memory using cycle stealing. The words are assembled from a device that transmits characters at a rate of 2400 characters per second. The CPU fetching instructions at an average rate of 1 million instructions per second. By how much will be CPU slowed down because of DMA transfer? Each character is of 8 bits. Now let's see what question is trying to say.
Generally, between memory and input-output device, CPU act as a bus in order to interact with input-output device. Here, in our case, CPU is being replaced by DMA in order to transfer characters from input-output device to memory. Until DMA completes a transfer of characters from input-output device to memory, CPU will be in an halt position or will be in an idle condition, which certainly implies CPU will be slowed down. The time for which CPU will be slowed down each time is equal to time required for DMA to transfer input-output characters to memory. Now, breaking our question, we have our computer requires 1 second in order to fetch 10 to the power 6 instructions. So, for one instruction, it will require 1 upon 10 to the power 6 second, which is equal to 1 microsecond. Now, from device which we are interested to transfer our data with the help of DMA to memory has a rate of 2400 characters per second. Now, for one character, it requires 1 upon 2400 second. For two characters, we require 1 upon 1200 second because we have 16-bit words, which is nothing but two characters. Now, 1 upon 1200 second is equal to 833.3 microsecond, which is nothing but slowed down in CPU or the time required for DMA to transfer characters from input-output device to memory. Now, in order to find its rate, just we will reciprocal it 1 upon 833.3 equal to 0.012. Now, to find percentage, we will just multiply it by 100, which gives 0.12%. So, this is a percent where CPU will be slowed down. That's all. Thank you.
I hope our video helped you in some way. Thanks for watching.